y1 and y2. And let's define z as just y2 inverse, y1, y2, y1 inverse. And this follows through.
So you can formulate the conjecture also in terms of the y formula.
Yes, exactly. And this is exactly what I'm going to do. This is exactly what I'm going to do. And so the conjecture now, I can formulate this as, so now that's another, so the conjecture now looks like this, that, so let just y k plus 1 z, y k minus 1 plus. Okay, then yk are, so all yk's are Laurent polynomials in y1, y2, and z. Well, actually in y1, y2, but I would like to keep z separate. So let me note that we work with, actually in this ring. Well, for simplicity, let the rational numbers. And this is actually a division ring. And this follows from Marx's theory. Well, it's a very special case, but at least you can actually divide here. Now, but so what I have here, I have basically only this. Now I would like to exchange yk minus 1 with this one. And lemma, which is actually very simple, says that I have yk plus 1 z yk equals yk plus 1. So I have to repeat 3, but now all I have is just this identity, so these formulas, and the formula for z.
But z is defined by this.
Z and z is defined by this.
It's more convenient to keep z.
Yes, yes. So and you will see why. Now then another thing is that also that I have to prove this. And this is how I actually interchange yk minus 1, yk plus 1, but so you have to be careful not to put z. Again, in the commutative case, when z equals 1, you have nothing. And just in general, actually, this can be even generalized. And you can write, for example, this. Plus 1 plus some 0 to m. And again, so this is more or less simple algebraic exercises. So nothing. All right. Now, let me formulate so the theory. And the theorem says that for any integer k, so you have the following formula. Okay, so now that's by using actually this, so this lemma, it's relatively easy to prove this theorem. So this is just now why this theorem actually proves. Why this theorem actually proves.
Oh, because the minus sign you cannot prove positivity.
Yes, because of minus I cannot prove positivity, but I have this, you know, there's nice recurrence. And then how to prove this, that's this, so then, okay, I already have y1 and 1 and y2, 2. Then I can get 1, 3 using this Laurent. So this, actually, this expression. So this is just Laurent polynomial. Then I can get y4 using exactly. Okay. I should actually get y0, which is also possible, but this is Laurent, okay? Because I can go back and forth. So this is Laurent. Then y4 is just a polynomial. It's just a polynomial.
But the
in all this.
The index gets, I understand, the index gets higher. The k, you try to.
Okay, so this is a polynomial formula, right? So if any of these guys are Laurent polynomials, then this guy is also Laurent polynomial.
But it's induction on k, so k is to go forward. Here.
Oh, I'm sorry.
Yeah, it's 4.
Oh, that's 4.
Yeah, like that.
Oh, I'm sorry. That's 4.
No, that's not okay. Let's keep it tracing.
Okay, that's 4.
I understand.
That's 4. Sorry
Now
about
I got
this.
it.
And now you see that this is.
Yeah, now I understand.
And so now you see. And so basically that's this solves the conjecture if you do not demand positivity. This formula does not positivity.
But there may be other more complicated ones, similar with plus.
Maybe, which actually, so we tried a little bit, but then we abandoned this. But actually you can generalize this because actually in in this formula you can add some coefficients and you can just add some coefficients to this. There may be generalization, but this is basically this one. Now I think that I have like 8 minutes. All right, so then maybe I will just show you by using an example how to prove such things, which is actually.
In the commutative case, it's much simpler. Then that is 1. Z is 1.
In the commutative case, Z is 1.
It was non-deformed, the commutative case?
I'm not sure. The method of proving Laurent phenomenon was known, that you have to find a polynomial expression connecting just twice with this. So this was known. But, I'm not sure if the polynomial was written in this. Okay. So let's just consider simple example when R1 plus R2 equals 2. Well, just maybe I'll try to prove this. So what I have here is just this thing. Let me see. This is just given. So this follows from Lemma. And actually I want to prove that, so let me put k equal 0 here to moment effect. Z. That's the special case of this formula. So let me start the proof. So first of all, this is just, so this immediately follows from this immediately follows from just from this formula. Okay, then I need a trick. So I have this expression. Okay. And I will just rewrite y2 inverse in a crazy way. Let's go. Then y4 times z can be -1, comes from here. Then I have to multiply this by y2 inverse, but I will replace this by this expression. Okay. Now I already have this. So that's part of this. But then I have y2 inverse times and now I want to show that this expression actually is divisible by y2. And so let me just do this. So I will write this in the following form. here I replace by my lemma. I'll replace this by so the result is like this. And let me write that this in this form. Here, this can be replaced by y2z squared. So this is divided this. Here I can exchange y1 and y2, so I have y2, y2z, y1, and then times. Well, oh, I'm sorry, I forgot this. Okay, and then the rest is, so I can then divide everything by y2, and then it's just to see that I'm getting this formula. So the only trick is here that you have to replace y2 inverse, but you have to replace it wisely. Don't know how and where. But again, so this is just basically this is a high school exercise. That's
So clever high school kids. Very clever.
Well, right. Okay, so that's I will stop according to the seminar rules.
Thank you very much. Professor, I'll be glad to answer questions in private.
Yes. Oh, I'm here. So,
Yeah, beautiful.
thank you.
So, when you probably had on motivation, I mean, this trick, how you get a trick? By trial and error, or you had on deeper reasons?